Okay, great. My presentation is Game Theory and LLMs, Enhancing Strategic Decision-Making in AI Systems, a deep dive into the intersection of strategic interactions and large language models. Okay, so large language models, or LLMs, have revolutionized AI, showing potential in complex reasoning tasks. Strategic reasoning is a distinct form of reasoning crucial for understanding and navigating complex multi-agent environments in physical and social worlds. It involves choosing optimal strategies while considering and influencing others' actions. Game theory provides a foundational framework for analyzing such strategic interactions, which is becoming increasingly vital for LLM development and evaluation. John von Neumann's work in the early to mid-20th century established game theory as its own independent field. So my research questions: how can game theory enhance the strategic reasoning of LLMs? What are the limitations of current LLMs in game theoretic settings? Which game theoretic methods can improve alignment, interpretability, and adaptability in LLMs? So the methodology, game-based environments. An overview: to assess LLM strategic capabilities, researchers deploy them in various game-based environments. So with game theory, I might ask, what is game theory? Game theory is a study of strategic interactions among rational decision makers. Key components are players, strategies, and payoffs, and applications across economics, politics, biology, and AI. So there are bargaining games, two-player repeated games, multiplayer games, zero-sum games, and negotiation games. Zero-sum games basically are a situation where one person's or entity's gain is directly equivalent to another's total gains, and they're added, and total losses are subtracted, and the sum is zero. Negotiation games, basically players make deals, build alliances, and strategically cooperate. Observed behavioral features. Key behavioral features of LLM-based agents. Pro-social bias. LLMs frequently exhibit pro-social cooperation over purely rational, self-interested game theoretic outcomes. Bounded rationality. LLMs frequently deviate from optimal strategies, particularly in tasks requiring complex probabilistic reasoning or adaptive play. Prompt sensitivity. LLM behavior is highly sensitive to how questions are phrased and the contextual cues provided in prompts. So specialized benchmarks. The need for dedicated evaluation. Traditional NLP benchmarks are often insufficient for evaluating LLMs in autonomous agent roles. Specialized benchmarks offer controlled environments to assess specific aspects of LLM behavior, from pure rationality to complex social interaction. Examples of specialized benchmarks: GT-Bench, designed for game theoretic evaluations, primarily assessing whether LLM decisions align with theoretical, specifically for identifying biases in AI agents using game theory, examining fairness, biases, and prompt sensitivity. Smart Play is a benchmark for evaluating LLMs as intelligent agents, which highlights their sensitivity to prompt framing and contextual cues. And LLM Arena places LLMs in dynamic multi-agent settings to test higher order recursive reasoning, coordination, and deception. The results: LLMs favor fairness and cooperation. Key finding: LLMs consistently lean towards pro-social behaviors in strategic games. They have high cooperation rates, human-like bargaining, tendency towards fairness, cooperator strategy, and positive emotional influence. Some weaknesses in probabilistic reasoning and consistency, challenges and deviations from optimal strategy, deviations from optimality, mixed strategy failure, strategic inconsistencies, and performance drop due to bias. Game-theoretic methods for improvement. Game theory offers concrete methods to enhance interpretability. The Shapley value quantifies the contribution of individual components, such as tokens, data points, layers, to an LLM's output, providing principled measure of interpretability. Input attribution, token SHAP, text gen SHAP, measures the importance of individual tokens or source documents in influencing model decisions and summaries. Training data evaluation, data Shapley, Shed, and SCAR evaluates the marginal contribution of each training sample or data set to overall model performance. Probing internal components, SVNUP, Shapley head values, assesses the contribution of architectural elements like layers and attention heads for model optimization and compression.
Dr. Foley, just one moment. If you might want to turn your camera off to save the bandwidth. You're freezing up a little bit. It might help. Is that okay?
Oh, I'm sorry about that.
That's okay.
Yeah, that's fine. It's probably because it's Thursday and so many people are probably streaming a football game. Sorry about that. All right, I'll turn off my camera here. Okay. Results, game-theoretic methods for improvement, aligning general preferences, NLHF, Nash learning from human feedback, models alignment as a two-player zero-sum game, allowing convergence to a Nash equilibrium under general preferences without explicit reward modeling. Self-play preference optimization, SPO, and direct Nash optimization, DNO. These methods train a policy against itself using win rate scores or a regression-based objective, demonstrating robustness to complex human preferences. And the Nash was a mathematician, John Nash, who was an American scientist and a mathematician who came up with the Nash equilibrium, by the way. Achieving dynamic adaptation. Self-play, the spin framework, LLMs generate their own training data by playing against previous versions of themselves, creating a curriculum of increasingly high-quality data, and refining strategies, such as in negotiation. Evolving reward signals, adversarial preference optimization, models the interaction between the LLM and its reward model as a dynamic game where the reward signal co-evolves with the policy, preventing reward hacking. Real-world applications and risks. Promising applications are autonomous systems. Game theory algorithms are used in autonomous vehicles to anticipate and react to unpredictable behaviors of other drivers. Financial trading bots using game-theoretic models to simulate adversarial market conditions and adjust strategies against competitors. Cybersecurity, AI systems leverage game theory to detect anomalies, predict intrusion strategies, and synthesize optimal defense strategies against attackers. Negotiation and diplomacy. AI assistants can simulate optimal negotiation strategies in business and politics, guiding decision-making in multi-scenario environments. Some of the associated risks: bias and hallucination. LLMs are prone to hallucination and flawed logical inference, especially without external guidance. Fragile strategic acuity. In the economic games, LLMs' strategic abilities can be fragile and lack robustness, often failing to consistently achieve equilibrium strategies. Ethical risks. Emotional prompting exposes significant ethical risks by revealing biases in human alignment, potentially leading to unexpected drops in cooperation, even under positive emotional influence. And undermining reliability. These issues can undermine the assumption of a stable and reliable oracle or solver in game-theoretic applications. And in conclusion, recap game theory's roles in LLM decision-making. Structured analysis and enhancement. Game theory provides a robust and structured framework for analyzing, evaluating, and enhancing the decision-making processes of LLMs in complex, multi-agent environments. Bridging human and AI behavior. It is crucial for equipping AI with social attributes, making them more intellectual, responsible, and empathetic by formalizing how agents interact strategically. The dual nature of LLMs, interpretability and bias. Human-like interpretability. LLMs offer unique explainability through their text-based reasoning processes, which simulate human thought, making their decisions more transparent. Inherent biases. However, LLMs introduce systematic biases, positional, payoff, behavioral, and emotional susceptibilities from their training data, which can lead to deviations from logical reasoning and optimal performance. In new evaluation metrics, these biases highlight the inadequacy of traditional evaluation methods and necessitate the development of new custom-developed evaluation frameworks and metrics specifically tailored for neural network-based agents. Future research directions, key areas for advancement, cooperative mechanisms, focus on integrating cooperative game-theoretic principles into LLM training. Scalable and robust training methods, improve the robustness, stability, and efficiency of game-theoretic methods like shapely value, calculation, and self-play, addressing computational challenges and variance. And domain-specific safeguards and ethical alignment, address and mitigate the problem of bias and hallucination, ensuring the correctness and logical consistency of LLM-generated content in game-theoretic applications. Develop new evaluation metrics that are robust, interpretable, and operationally meaningful, specifically designed for LLMs rather than repurposing human cognitive tests. And these are my references. I'd like to open up for the floor to questions. Thank you.
Ideally, post your questions in the chat box, and my esteemed colleague, Dr. David Johnson, will field those for you. Looks like we've got one from one of my former students, Sneha. Could game-based feedback loops train LLMs to recognize and self-correct hallucinations in real time?
Yes. You can develop a loop where the newer iteration of the LLM can play against itself in earlier versions, that can be achieved. Were there any other questions?
I don't have a question, but I did send you market a project that I was working on. It's based on reinforcement learning, and I've used some reward and punishment framework from game theory. I would really like your feedback on it.
Okay. Would you like to send it to me or?
Yeah, I just sent it on to you a direct message, but I'll just send it to you everybody. So
Okay, another question. How do you get LLMs to play against itself to generate new data? Is this a conversational approach?
You can initiate a game in which the newest iteration of the LLM plays against earlier versions to improve and enhance some of the abilities. Now, with I don't want to really call it a feedback loop. That's not really the right phrase for it, but that can be done through the different games that are available.